Good afternoon. This file contains the pre-lecture notes for class on Tuesday, October 22nd. The relevant reading is contained in the first half of the Carey Chapter 9. This week we're going to move away from substitution and addition and elimination reactions with regard to alkenes to move to a new functional group, the alkyne functional group. Takeaways from this pre-lecture include alkynes themselves, which are carbon-carbon triple bonds. We'll talk about their structure and their reactivity in the first half of the pre-lecture. We'll also talk about alkylation and carbanions. These are two new concepts that we've not talked about before in the class. Alkylation is the concept of adding an alkyl group to a parent compound. We've never done anything like this before. We've always substituted functional groups on alkyl halides or on alcohols. Today we'll talk about adding alkyl groups to alkynes. We'll also talk about the concept of the carbanion. This is a carbon atom that bears a negative formal charge. To date, in the past 8 weeks of the course, we've only ever seen carbon atoms as neutral, radicals, or carbocations. This week we introduce the concept of a negatively charged carbon anion. You should already guess that a negatively charged carbon atom is capable of acting like a nucleophile just as much as a positively charged carbon cation is capable of acting as an electrophile. To name alkynes, we use the same IUPAC naming system that we used for alkenes. The simplest alkyne, which contains a triple bond between two carbon atoms, is called acetylene or ethyne. Both are acceptable, ethyne being the IUPAC name. All higher order alkanes are named exactly the same way we did for alkenes, except instead of using the ene suffix, we replace it with the yne suffix. So, a three carbon compound containing an alkyne would be propyne. A four carbon compound containing an alkyne would be butyne. Notice that we don't need to use the one if we don't want to. We can just say butyne and we would recognize that as a four carbon containing alkyne. Down here we see that the rules apply for an internal alkyne. If the alkyne is at position 2, it becomes a 2-pentyne, as we have here. All the rules that you've already learned with regard to identifying the number of substituents and their locants apply the same as they do with alkenes. So before we get into the structure and reactivity of the alkyne functional group, let's pause for a minute and remind ourselves why it is that we're learning this. So alkynes are important in two different arenas that may be of interest to you. First, if you notice going around the city when new buildings are going up and you see the guys hanging up the skyscrapers with blowtorches in their hand, they're using alkynes as the primary fuel source. These are called acetylene torches. As a matter of fact, you can buy them yourself at Home Depot to do small projects at home. Alkynes have a tremendous amount of energy stored in their triple bonds, which is released upon formation of water and carbon dioxide in a combustion reaction, which makes an alkyne functional group the fuel of choice in blowtorches. Second, and perhaps of more interest, is that alkynes have recently been discovered to have very potent anti-tumor properties. Notice in these two compounds, dinomycin A and neocarcinostatin, that each of them contains this unique functional group that has two alkynes in it. This is an ene-diene. Notice alkyne, alkene, alkyne, over here again, alkyne, alkene, alkyne. This particular functional group is highly reactive as an anti-tumor agent. In fact, it's even referred to as a warhead by medicinal chemists because of how reactive it is as an anti-tumor agent. So there is some relevance to alkyne chemistry, which is why we include it in the 232 curriculum for those of you who are interested either in building materials or in medicinal chemistry. So let's get to the structure and reactivity of the alkyne functional group. Remember that alkyne carbons, because they have two pi bonds and one sigma bond between the two carbons and one remaining sigma bond between a carbon and either an hydrogen atom or an alkyl group, are linear. They have a linear geometry. So an alkyne functional group can be thought of sort of as a straight chain, rigid functional group, which is different from the planar sp2 hybridized carbons that you've seen in alkenes and different than the tetrahedral sp3 hybridized carbons that you've seen in alkanes. So, To form a triple bond, we have to have a carbon atom undergo sp hybridization. Once again, alkenes are sp2 hybridized, their vinyl carbons are sp2 hybridized, and in alkanes, those carbon atoms are sp3 hybridized. Alkyne carbon atoms are sp hybridized, which means that one s electron orbital mixes together with one p electron orbital to produce two sp orbitals and leave behind two half-filled p orbitals. Those two half-filled p orbitals will each go on to become the two pi bonds, and the two half-filled sp hybridized orbitals will form the two sigma bonds around the carbon atoms in the alkyne functional group. As you can see on this slide, the two carbon atoms are joined together by the overlapping of their sp hybridized orbitals to form a shared sigma bond between them. The remaining sp hybridized orbital on each carbon atom is available to bond with either a hydrogen or another carbon atom as needed to form the compounds that we're interested in. Those pi bonds, remember, are above and below the internuclear axis between the two carbon atoms. The second pi orbital is orthogonal to the first pi orbital, going at a 90-degree angle also on either side of the internuclear axis, that internuclear sigma bond between the two carbon atoms. We can see that this structure gives the overall linear shape to the alkyne triple bond, which is very different than the planar shape we've seen before with alkenes. Notice that what is similar between them, again, electron density is all between the two carbon atoms contained within those pi bonds, as it was between the two carbon atoms in the alkene functional groups that we looked at before. As with alkenes, the addition of alkyl groups to alkyne functional groups stabilizes the functional groups. Notice the relative differences in the heats of hydrogenation between these two compounds. The monosubstituted alkyne functional group is higher in energy than the disubstituted alkyne functional group, as we can see here. This is for the exact same reasons that we talked about with regard to alkene stabilization from alkyl substituents. Hyperconjugation and induction stabilize alkynes in exactly the same way that hyperconjugation and induction stabilize alkenes. So let's begin by talking about the chemistry of alkyne functional groups by talking about acidity. Remember that alkanes in general are not acidic. They have very high pKa's, which means that they are unwilling to give up their protons. Alkenes, by contrast, are more acidic than alkanes, and alkynes are much more acidic than alkenes. In fact, the pKa of alkynes is low enough that alkynes can act as weak acids by donating their protons to nucleophiles. This brings up the H in the I share mnemonic that we covered earlier in the semester. Those are induction, size, hybridization, aromaticity, resonance, and electronegativity. In the beginning of this semester, we talked about only 4 of those concepts. Now we can talk about the 5th one, which is hybridization. As we can see here, the hybridization of a carbon atom affects the acidity of the organic compound. sp3 hybridized carbons are much less acidic than sp2 hybridized carbons, which are much less acidic than sp hybridized carbons. The reason for this is because the electrons in the sp hybridized orbital are much closer in s character and are more strongly held to the nucleus of the carbon atom in an sp hybridized carbon than they are in sp2 and sp3 hybridized carbons. This means that an sp hybridized carbon is much better able to stabilize a negative charge than an sp2 or sp3 hybridized carbon, making alkyne functional groups weak acids. Given that we know that terminal alkynes bear acidic protons, we can ask ourselves the question, how is it that we deprotonate these terminal alkynes? For example, if we want to prepare a solution containing sodium acetylide, notice that this is ethyne that's been deprotonated. How is it possible that we can create this compound? How do we pull that proton off knowing that its pK is 26? Okay. One reasonable approach may be to combine together a strong base together with the terminal alkyne in order to produce the carbanion. Right? Remember, however, that the equilibrium in acid-base reactions lies in the direction of the weaker acid. Compare the two acids on each side of this reaction. The ethyne proton has a pKa of 26, while water, which is of course the conjugate acid of hydroxide anions, has a pKa of 15.7. Water in this case is a much stronger acid than ethyne is, which means that the equilibrium here lies to the left. This reaction will not produce the carbanion that we're seeking to produce. The solution to our problem, of course, is to use a much stronger base than sodium hydroxide in order to accomplish this reaction. Your book introduces you to sodium amide as an extremely strong base that can accomplish the deprotonation of a terminal alkyne in order to produce the carbanion. The reason that this reaction is favorable and lies to the right is of course due to the fact that the pKa of the terminal alkyne is much lower than the pKa of the conjugate acid of anions. Notice of course that the conjugate acid of an amide anion is ammonia. This base is strong enough to deprotonate the alkyne in order to produce the carbanion. Notice, this is a negatively charged carbon atom. We've seen before that negatively charged atoms are capable of acting as a nucleophile, and later in the pre-lecture we'll see cases in which we can use this carbanion in order to alkylate an alkyne. So, given that we know that alkynes are acidic, there are several different types of reactions that we want to introduce in this chapter. Although this looks like a lot of reactions together on one slide, notice that I've separated them into two different types of reactions. One is the preparation of the alkyne functional group itself, and the second set are reactions of the alkyne functional groups with other reagents. Happily, most of these reactions you've seen before with regard to alkenes. Although they'll look different and the reagents may be slightly different than those you've seen before, the mechanisms are almost identical to what we learned about with regard to addition and elimination reactions. For today, we'll talk about two of these reactions, alkylation reactions and elimination reactions. So to prepare alkynes, there are two main approaches that we use in the synthetic laboratory. One is carbon-carbon bond formation through an alkylation event of acetylene or other terminal alkynes. The second group is a functional transformation consisting of elimination reactions that you've already seen before in this class. So, given that we can deprotonate a terminal alkyne using a very strong base like sodium amide, we can create a carbanion that acts like a nucleophile in SN2 reactions with alkyl halides. Think of this carbanion as any other nucleophile that you've seen before. It has electron density around it, which is capable of attacking electrophile to displace a leaving group in an SN2 reaction. This type of reaction is known as an alkylation reaction because we're adding an alkyl group to an alkyne functional group. We are alkylating the alkyne functional group. In effect, this allows us to take a terminal alkyne and produce an internal alkyne in cases where we begin with a terminal alkyne that already contains an alkyl group on it. So, let's take a look at a series of steps in a synthesis that involves the alkylation of a terminal alkyne. Here we have a alkyl chain that contains an alkyne functional group at the end of it. There's our acidic proton at the end of the alkyne. We treat this alkyne with a very strong base such as sodium amide in ammonia as a solvent to create the carbanion. From here to the carbanion, we can add any primary alkyl halide, in this case methyl bromide, to alkylate the carbanion to produce an internal alkyne. Notice that this alkyne functional group is internal with carbons coming off both ends of the alkyne carbons. Notice, this reaction is only effective with primary alkyl halides. Remember that SN2 reactions prefer to react around alpha carbons that are not sterically hindered and contain the least number of alkyl groups around them. With regard to the alkyne functional group, alkylation only works in cases where we have primary alkyl halides. This is because alkynes that are converted into carbanions are very, very strong bases. And remember what happens when you combine together a strong base with a secondary or tertiary alkyl halide. You don't substitute, instead you eliminate. So if you want to do an alkylation reaction, remember that the functional group that you must work with has to be a primary alkyl halide. The second way in which we prepare alkynes is through double dehydrohalogenation reactions. Remember, you already know what a dehydrohalogenation reaction is. In fact, this is the first type of beta elimination reaction that you learned about, which involves the removal of a hydrogen atom and a halide functional group to form a pi bond. A double dehydrohalogenation involves eliminating two beta hydrogens and two halide leaving groups to create two pi bonds, which are necessary to form the triple bond in an alkyne. One way to think about this is if we consider either geminal dihalides or vicinal dihalides, geminal dihalides being dihalides that are shared on one carbon. They're called geminal because they're considered to be twins, like Gemini. They're both contained on the same alpha carbon. Vicinal dihalides, you've already seen this before. Vicinal dihalides are two halogens that are on carbons that are neighbors of one another. They're in the vicinity of one another. Notice, on both of these, I can do two beta eliminations. For the geminal dihalide, I can take off this beta hydrogen and this leaving group here, as well as this beta hydrogen and this leaving group here. That would leave me with two pi bonds, which combined together with the sigma bond already existing in this compound would produce a triple bond. Over here, the vicinal dihalide can also undergo two beta eliminations. We can take off this beta proton and this halogen here, or this beta proton and this halogen here, also to produce an alkyne. So let's take a look at a reaction that involves converting a geminal dihalide into an alkyne. Notice what I have. In this case, I have a dichloride that is a geminal dichloride because both of the chlorine atoms are attached to the same carbon. We use 3 equivalents of sodium amide and ammonia, and we quench it in a second step with water to produce our alkyne. This reaction involves a double elimination that converts the sigma bond in the straight alkyl chloride into a triple bond in the terminal alkyne in this case. Notice that your book points out the need to use 3 equivalents of the base in order to accomplish the double dehydrohalogenation. You may ask yourself, why don't I just need 2 equivalents since I'm only taking off 2 beta hydrogens? This is a good question. Notice that once the alkyne forms, you have an acidic proton. This proton is much more acidic than either of the 2 beta protons in the original starting material. Note this is an alkane where this is an alkyne. The pKa of this proton is much lower than the pKa of these 2 protons. As such, when any single molecule of this alkyne forms, it will react much faster with the sodium amide base in order to deprotonate since its pKa is so much lower. We add the extra equivalent of the sodium amide in here in order to deprotonate all of the alkyne as it's formed so that the remaining base can react with the beta hydrogens that are in the starting material to produce our final product. The water used in the second step quenches the reaction by protonating all of the deprotonated compounds, getting rid of the negative charges. In effect, it puts the H back on the carbanion to produce the terminal alkyne. Here are the different steps involved in this reaction so that you can see them all laid out. In the first step, we use a sodium amide base in order to deprotonate one of the beta hydrogens to produce the alkene. In the second step, we remove the second beta hydrogen to produce the alkyne. The third sodium amide base, of course, deprotonates the alkyne in order to produce the carbanion, and the water molecule is available as an acid in order to reproduce the alkyne, which is our target product. This process works equally as well for vicinal dihalides. In this case, we're removing a beta proton from 2 different carbon atoms to produce our terminal alkyne. Remember, this is a double beta elimination, so this hydrogen is removed at the same time as this bromine, and one of these 2 hydrogens is removed at the same time as this bromine over here that is in the beta position. So that is it for this pre-lecture on Tuesday. We covered the structure and acidity of the alkyne functional group and the preparation of alkynes through both double eliminations as well as alkylation reactions. On Thursday's pre-lecture, we'll talk about the reactivity of the pi bonds in the alkyne functional group itself and their reactivity with other reagents that we've seen previously in the semester. With that, make sure to do the relevant reading in your Carey textbook and come to class prepared to apply what you've learned.